So let's move on. So finally, we are in chapter 6. It's about multiple regression. So today's theme is very simple. Today I explain why we need a multiple regression. Okay? A multiple means that you have more than one independent variable. So why we need more than one independent variable? Why we like to have more? So this is a story. It's a story in the lecture notes, and a story in the textbook too. So I explain this story, and I'm going to give you a quiz. Okay. So this example, y is your wages, and let's say that x, or maybe just x1, one of independent variable is your job. So the idea is that your company sometimes have some kind of program, education program for employees, okay? It can be just 1 day, very short session. It can be 3 days long session, or maybe can go at as long as 2 months. You just basically you're sent to some location, maybe campus, and then you become a student again for the next 2 months. Because it is costly, the companies likes to know what is the effect of this job training program. Okay, it's kind of very common question. So suppose that you are a consultant of your company, or maybe you're just outside consultant for some companies, and the company wants you to find out the effect of their job training session, job training program. Okay. So the idea is you collect their wages, and some people get the program, some people don't get the program. So you like to compare. Right? So you come up with this regression model. And then you explain that this beta 1 is the effect of the job training program. Does it make sense? So, it's just to make it simple, let's suppose that this is a dummy variable. So if you get a job training, then you get 1. If you don't, you get 0. So the idea is you compare 2 groups after maybe a year or 2. And then you measure the performance in terms of their subsequent wages. Okay? So everything looks fine. So, when x1 is a dummy variable, the coefficient is simply the effect of being 1, right? So being 1 means you participate in the job training program. So it makes sense to say that the beta 1 captures what you want. So you presented this, and there's somebody in the audience and complained, and basically the complaint is that there is another very important factor that is ignored in your study. Okay, the factor is maybe the productivity of each employee. Let's just call it x2. So the key story is that it's not that random that somebody go to the job training program and somebody doesn't. It's that over the time, he observed that the boss of the company actually knows who is productive and who is not. Okay? And then the boss tend to send the less productive persons into the program so that he or she can learn more from that type of education. Okay? So that is basically the criticism of your regression model. Now, the claim is, suppose that you just run this regression and get the outcome. So we like to ask, is this beta hat a good estimate of the effect we like to know? Suppose that's the question. And the criticism of this regression is that there's this hidden factor, the productivity of each individual. And somehow these two things, x1, the dummy variable of job training session, and x2, are correlated in a certain way. So in his story, there is a negative correlation, right? If a person is less productive, he has more chance to get the program, right? To be in the program. Now think about this. Does it cause any problem in your regression estimate, intuitively? Now, let's think about some ideal case, ideal situation, where the boss actually throw a coin randomly, and if it is head, he doesn't go to the program. If it is tail, he goes to the program. One of his employees, okay? Then on the average, the groups whose x1 is 1, so let's say that that's on my left-hand side, and the group who has 0 of x1, who is on my right-hand side, must have some kind of equal qualification, right? On average, you just throw a coin. So individually, you may have some better person here and there, but the average quality of these two groups about the same, right? So before the job training program, you have two groups of individuals that have the same ability, same qualification. And suppose that this job training program increase your human capital, therefore your productivity, therefore your wages later, right? So this group get the program and this group does not get the program. If the program is useful, after 1 year, your wages is going to be like this, right? And the difference is the effect of the program. So that's when everything goes very smoothly, very nicely. Now suppose that his story is true. The boss actually knows everybody's productivity and send the least able persons into the program. What happens before the program? We are not comparing the same kind of people, right? If you know that somebody is in the program, it means that on the average, he is less able person. If somebody is out of the program, he is more able person. Now suppose that the productivity is enhanced, increased by the program. But the starting point is like this, different. So even if the program increases the productivity later and the wages later, the difference may not be exactly the same as the true effect. Do you get the point? Somehow, I don't like the explanations, but let me try again. Now, this is when the program is assigned randomly by throwing a coin. And suppose that the program increases the productivity and the wages this much. Okay? So this is before anybody gets the program, and this is after this group gets the program. So if you just measure the difference between two groups, you actually measure the effect of the program, right? Now, suppose that this assignment is not random. And before the program, the situation is like this. In this group, if you know that somebody's in the program, you kind of know that he sucks at the job. So it's a collection of less productive employees. And this is more productive employees, right? Now this is before the programs. So after program, suppose that the program's tree effect is quite positive. Now, after 1 year, you compare their mean wages and may not see much difference. Okay? It is not because the program is useless. It is because we failed to compare the same kind of people. Okay? So in that sense, the tree effect is on yellow, but the measured effect from the regression is this small, is red. So somehow your regression underestimates the tree effect. It has a problem. This kind of problem is called the omitted variable bias. Get the point? Okay, let me give you another example. Can I erase this? Maybe just erase this. Now, one of the very common equations in economics is on the left-hand side, there's wages, right-hand side, there's education, and you like to measure the effect of education. Okay? So everything kind of looks smooth. But again, you can offer the same criticism. Suppose that there is X2 that is not used in your research, and let's just call it ability or competence. And the story goes like this. When you see two different kinds of people with different level of education, they are not the same kind of people. Maybe just one possibility. Able person choose to get more education, and less able person choose to get less education. Why? There's a lot of theory, okay? But theory is outside of econometrics. It's more like a labor economics. There's a lot of model that explains why. But suppose that that's the case. More able person, maybe it's because it's less costly, less painful to get a bachelor degree, master degree, or even more. Okay? So more able person tend to get more education. Suppose that that's the case. So in this example, the covariance between x1 and x2 is positive, right? Just purely by assumption. So if you have more competence, you tend to get more education. Now, the regression you're using is something like that. Now, the question is, you run this regression and get beta 1 hat. Suppose that the education has a positive effect on your income, on your wages. Okay? But we ignore this x2, competence, ability. Now, does it makes you underestimate the effect of education or overestimate the effect of education? Think about these pictures. Again, so this is the group of people who get more education, less education. If you just mix them randomly, just assign some people to one group and ask this person to get this much education. Okay, you get college degree. And then you randomly choose another set of people and ask them only get high school degree. If that's the case, that we are comparing the same kind of people on average, and the difference between two groups is the effect of education, right? But if more able person choose to get more education, then even before anybody take the college education, things can be quite different. So this group may be simply more able, more competent, which increases wages, by the way. Right? Now, if education enhances it, the estimated effect, the difference between two groups, that's what the regression measures, right? Can be bigger than the tree effect. So in this case, we overestimate the effect of education. So there are tons of examples like that, okay? And you will see a lot in the quiz and in the exam. Okay, so let's formalize this idea because it's just all about the story. And we can use some mathematics and to make it much more precise. So let's go back to the first example, this example, okay? So Y is wages, X1 is job training program, X2 is productivity. Now this is the regression that you actually used, okay? And this regression model is criticized. To overcome this problem, the best solution is to find out this X2 and include it. And it will solve the problem. But for now, let's just compare these two equations. This is called the short. Now, I call it a short model because the regression is shorter. And there, the regression is longer, okay? So in our example, in this particular example, this is the regression that we are supposed to use. But because of some problem, we actually end up using this one. So long regression model is the regression model I really like to use. But perhaps because I don't have any data about people's ability, right? An insider, everybody's boss may know because they have years of interaction. But you're just an outside consultant, an economist. You have no idea who is able, right? X2 is not a part of your information. So maybe that's why I have to use this short model. Okay? And then suppose I run this regression and get the estimate. And the question is beta 1 hat equal to the beta 1 of the tree effect over there? So we are kind of assuming that this is the true relationship between variables. And this is the kind of relationship I assume for convenience because I don't have X2. So this is the question. Now one thing we have to understand is, so ideally I like to include X2 in the model, but I failed. Then this X2 must goes to my errors, right? So everything I did not include, did not control, goes to the errors in my actual regression model. So UI okay. From the textbook, there is a formula, and this is the formula you have to memorize. And basically, the formula says beta 1 hat. So when I say beta 1 hat, I only run this regression. I couldn't run this regression. There's no X2, okay? So when I say hat, the actual estimate, I meant a short model. Actually goes to beta 1 plus some bias And this bias is called the omitted variable bias. And how the bias look like? And this is how the bias look like. So what do I mean by goes to? So what I mean is that as you increase your sample size, then your beta 1 hat approaches to this quantity. This is a fixed number, unknown number. This is a fixed number, unknown number. So sum is just a number, right? So as you increase n, the sample size, beta 1 hat is closer and closer to this thing. Now, let me explain this. What is this? That's the correlation between x1 and u in the model you actually used. So what is x1? x1 is the independent variable you used. So let's just call it included variable. It is included in your regression. What is u? u is the error of the regression you actually used. Okay? So we are talking about correlation between this and this. So don't be confused, okay? So that's the correlation part. Sigma u is a standard deviation of the error of the short model, the error of the regression that I actually used. And this is the standard deviation of x1, the included independent variable. Okay? So this is positive, this is positive. So the sign of the bias only depends on this correlation. Now, ideally, we hope that the bias is 0. There's no bias in our estimate. Then this is a good thing. The beta 1 hat, your estimate, goes to become closer and closer to beta 1 that you want to know, right? So that's the meaning of consistency. If this is 0, so you have a consistent estimate, meaning that if you provide a lot more information, your solution, your answers become more and more precise, which is a good thing. But if this is not 0, then we have trouble. Even if you increase your sample size, it becomes closer and closer to something that is a sum of true effect and bias. If the bias is much bigger than your true effect, then your estimate converges to something that we don't want to know. Suppose that this is 1.5 and this is 10. Okay? Your beta 1 hat is not converging to 1.5. It is actually converging to 11.5, which is kind of meaningless to us. So it's quite a serious concern, because you cannot solve the problem by increasing the sample size. So what is the direction of the problem? Let me just draw some picture. Now let's think about two cases. Now suppose that beta 1 is positive. The effect itself is positive. We have two cases. The first is when the correlation is positive. So suppose that the correlation is positive. Then your beta 1 hat, if n increases, become closer to your beta 1 plus some positive number, right? So as n increases, it's going to be bigger than the true effect. So this is the case you overestimate the effect. So this is our second example. And x1 is education. The omitted variable that I failed to include in my regression was the ability. If that's the case, the bias is positive, and the true effect is positive. So our estimate actually becomes much bigger than the effect of education. Maybe the true effect of education is just 8% per year, but your estimate can say 15%. Okay, so we shouldn't believe it. Second case is beta 1 is positive, and then correlation is negative. Then beta 1 hat becomes closer to true effect plus something negative. So it's going to be, your estimate becomes smaller than the true effect, and we say that we tend to underestimate our true effect. So this is the case for the first example, the job training. X1 is the job training program, the dummy variable. X2 is the productivity. And in that case, the bias was negative. So that's why we underestimate the effect. Now the tricky thing is when the true effect itself is negative, and suppose that the bias is positive, what's going to happen? Beta 1 hat is equal to the true effect plus some positive number, right? Minus number plus positive number. So it's going to be smaller than the true effect in a negative way. Do you understand what I mean? So suppose that this is 0. If your beta 1 is positive, the first case is here. So you overestimate. The second case is here. You underestimate. Now suppose that the beta 1 itself is negative. In the third case, when the bias is positive, your beta 1 hat will be somewhere here. It can be anything over here. So, no, what am I talking about? Is it correct? Minus plus plus number. So it has to be bigger, right? So it goes to some minus effect plus some positive bias. So that's case number 3. So effect is minus. Your estimate can be somewhere over. So I said beta 1 hat is bigger than the true effect, but its magnitude may be smaller. What I mean is true effect may be minus 5, and your biased estimate can be minus 2 or plus 1. Okay. Now the final case is if everything is minus, your estimate is going to be much smaller in the negative sense than the true effect. So we are in this situation. So in case 1 and 2, when the true effect is positive, we use this language like overestimate something, underestimate something, because it's very natural. But in 3 and 4, I don't know what is the natural choice of the words. But anyway, that's what is going on. Okay, just remember this picture, and remember that where the beta hat goes really depends on the original sign of beta 1. Is it okay? Okay. Now the next thing I want to do is to actually prove it. So why this is true? It's very simple. So let me show you why that has to be the case. So do you remember that the last week when we talked about this Gauss-Markov? So we actually play with this summation of everything, and it shows that Do you remember this? And actually, whether I have U bar or not does not change anything. If you don't remember this, perhaps it's because you missed a class, because you have something else, right? So in that case, just take a look at the lecture notes right before. But anyway, this is something we did together. So that's our beta 1 hat for any sample size n. Now let's increase sample size. What's going to happen then? Think about the denominator, which is easier. So what is this? Oh, to make it cleaner, I have to divide everything by n minus 1. What is this? This is a sample variance of x. Right? As you increase the sample size, it becomes closer and closer to the population variance. That's the meaning of consistency for the sample variance. Your estimate becomes closer and closer to the truth as you increase the sample size. So denominator goes to variance of x. Actually, this x is the x we actually use in the regression. It's got to be x1. Okay? And we're just not writing down the whole thing, but let's just put x1 here. This is the independent variable we use in our actual regression. Now, what is this? This is a sample covariance of x and u. Right? The sample covariance becomes closer and closer as you increase sample size to the population covariance. So that happens when you increase your sample size. Now, do you remember that the covariance is correlation coefficient times standard deviation of each variable? The covariance is correlation times standard deviation of x1, the first variable, and the standard deviation of the second variable, right? Now, this sigma x1 will be cancelled out by one of the sigma x1. So let me just erase it. So that's the formula. Okay? So it's very simple. Beta 1 plus correlation between the included independent variable and the error of the regression you actually used. And there's a two standard deviations that do not affect the sign of the bias. Okay? So that's the omitted variable bias formula. So really the whole thing is, if you figure out the sign of this correlation, you are done. You can say it overestimates, it underestimates. By how much? By this much. We kind of know everything. Okay? So let's talk about that. So how to figure out this correlation between the included variable and the error of the regression. The thing is that it is not always very easy to think about the correlation between the x and the error. Sometimes, just from my experience, I found it easier to think about this covariance instead of correlation coefficient. Let me tell you why. So here, this is one formula, and this is more like a simplified version of the first one, right? But sometimes this one helps. So let me just say second version of the omitted variable bias formula. which just depends on our first line. Let's think about this expression for y. So again, the sign of the bias only depends on the covariance, right? Because this variance is always positive. So when you think about overestimation and underestimation, you only worry about the sign of this covariance or the correlation coefficient. So let's think about this covariance more. What do you remember about these errors of the regression you actually used? The x2, the competence, the productivity was supposed to be in the regression, but it is out, right? It is omitted because we don't have that variable. If that's the case, it just automatically goes to the error, right? So maybe somewhere in your notes, you wrote down that u is equal to this quantity. Okay? So let's think about this covariance term. Now the law of covariance says that if you have a constant, you can just put it out, right? For the covariance, you just put out the coefficient. So don't be confused. For the variance, you have to square it first and put it out. But there's nothing like that for the covariance. Now this is the covariance of x1, the included variable, and e. E is the error of your true regression, the long regression mode. If the regression is true, if it has any truth in it, the error and all the covariates, independent variable, must be uncorrelated, right? This is what I mean. And this is actually true. And we are assuming that this is true, right? The regression assumption 1 says E given x1 and x2 must be 0, which is actually saying that, no, this is E. The error and one of these independent variables must be uncorrelated, both of the independent variables, right? So it's got to be 0. It's by assumption that the long regression is true regression. So from this calculation, we know that the bias will be 0. The bias is this term. The variance cannot be 0. And this is what it means. The bias will disappear if one of two things happen. So this covariance will disappear, which means the bias disappears if this is 0 or this is 0. So one of these two things is 0, then the bias disappears. Then we don't have to worry about the omitted variable bias. Okay? So your regression is fine. It's okay to drop x2. Now let's think about the example first. Example 1. So y was your wages, x2 was productivity, x1 was the job training program, whether you have it or not. What do you think about beta 2 in that example? So beta 2 is the effect of x2 on y. So effect of productivity on wages. Can we claim that it is 0? You cannot, right? Mostly it's got to be positive. Now, what can you say about this covariance between job training program and the productivity? The story was it is negatively correlated, right? So the one thing that I can say is that because of the two reasons, we had to worry about the omitted variable bias. Because we believe that beta 2 is not 0, and the covariance between the included variable and the omitted variable is not 0, then there should be a bias. Okay? Now, what is the sign of the bias in the first example? Again, beta 2 was positive in that example. Covariance was negative in that example. So beta 2 times covariance, which is the sign of the bias, must be minus, right? So your regression estimate converges to the tree effect plus something minus. So that's why we underestimate the tree effect. Now let's think about the second example. Your dependent variable was wages, x1 was education, x2 was your competence, your ability. Is beta 2 equal to 0? What is the effect of competence on wages? Is it 0? So, it's kind of reasonable to assume that if you're more able, then somehow people can figure it out. Your employer eventually figure it out and give you a raise, right? So it is not 0. It's actually positive. Is this covariance equal to 0? Assumption was it was not. Able person choose to get more education. There's the assumption. So again, we can say two things. Because this is not 0 and this is not 0, you have to worry about the omitted variable bias. Now what is the sign of the bias? Positive times positive. So the whole thing becomes positive. So your estimate converges to the effect plus positive bias. You overestimate. Okay? Oh, is it clear? Okay, so that's it then. So that's all I have to say. But anyway, let me just summarize the discussion so that you may just memorize this thing. So when you present your regression outcome, you always get criticized. There must be somebody who is claiming that you missed to consider this important variables. So therefore, your regression outcome cannot be trusted. Okay? So he may say that this is missed. Didn't consider the effect of this. So we have to know what to say. So somebody say x2 is omitted. Some kind of bad thing. So if somebody says, you have to think about two things. First of all, beta 2 cannot be 0, and covariance of included variable and excluded variable cannot be 0. Now suppose that you're on the defense side. You have to defend your short regression, okay? Omitting something. Somebody criticizes it. So what is the chance that you can defend your regression, your research? You either claims that omitted variable is not effective. It's not a determinant of the outcome. If that's the case, then you can forget about this omitted variable bias. You can omit that variable. Or the second chance is they are uncorrelated. Your included variable and excluded variable, they do not move together. If you somehow can show it, then again, you don't have to worry about the bias. Okay? So that's how you defend. Now, if you criticize someone's research, so somebody presents, but it's kind of crap, and he or she just miss a lot of these important variations here and there. So how do you criticize? So you have to make this argument. So you're missing this important variable x2 in your regression, and it is an important determinant, and there is a positive or a negative correlation between the omitted variable and included variable, so there must be an omitted variable bias. Okay? So that's how you actually attack or criticize someone's research. Okay, so if you want to know more exercises, some stories, A really good source is a textbook. There are a bunch of examples in the exercises in chapter 6. So just go to chapter 6 and start to read a few of those exercises. You'll find a bunch. Okay, I'll see you tomorrow.